This is Furry Elephant Lesson 5.
We're going to see what voltage and current mean and how they can be measured.
We're going to do this in class, too.
We'll also introduce some simple calculations.
Ooh.
We've seen that charges have different amounts of energy as they flow round a circuit. Wouldn't it be useful to know how much energy each lump of charge had? In our animations, electrical energy is represented by red stuff surrounding the black dots. Voltage is a measure of the energy, red stuff, carried by each coulomb of charge, black dot. These charges have lots of energy. We say that this side of the circuit is at a high voltage. In the middle of the bulb, the charges have less energy. We say that this point is at a lower voltage. These charges have no electrical energy. We say that this side of the circuit is at 0 volts. We've also seen that charges move. Another useful idea would tell us something about how fast they're moving. This is the idea of current. An electric current is a flow of charges. In metals, the current consists of moving electrons. Some liquids can also conduct. In this case, the current consists of positive and negative ions. A negative ion is any atom that has gained one or more electrons. A positive ion is an atom that has lost one or more electrons. In a liquid with salt dissolved in it, there are positive and negative ions. The positive ions move towards the negative terminal, and the negative ions move towards the positive terminal. Notice that they move slowly. They're already there before the circuit is connected, and they all start moving everywhere at the same time. The current will be small if the voltage isn't very big. Even gases can be made to conduct if the voltage is high enough.
Lightning, like a lamp, fluorescent lamp.
Examples of gases conducting are in sparks, lightning, and fluorescent lights. The process is complex, but the current when gases conduct consists of free electrons and ions. In this circuit, the charges are flowing quicker near the battery than through each of the bulbs. We say there is a high current through the battery. And a lower current going through the bulbs.
Okay.
So for voltage, think energy. For current, think movement. Let's look at how we measure voltage and current. Voltage is measured using a voltmeter. We can't measure the voltage at a point without comparing it with somewhere else.
So remember, it's potential difference.
That's why we talk about potential difference, or PD. Potential difference is just the difference in voltage between 2 points. voltage has nothing to do with flow. That's why we always talk of voltage across a component, or between 2 points. We never talk about a voltage through something.
Between 2 points.
The simplest way to connect a voltmeter is to connect the 2 leads first. We can then use it to sample the voltage between any 2 points. For example, we could measure the voltage across the bulb. We say that the voltmeter is connected in parallel with the bulb.
Bulb, voltmeter, they're parallel to each other. Okay.
Voltmeters are always connected in parallel with the component that you're measuring the voltage across. In this case, the voltage across the bulb is 6 volts. In fact, we can tell what the voltage should be just by looking at the battery and our animation. The voltage on the positive side is 6 volts, and the voltage on the negative side is 0 volts. So the voltage, or potential difference, from one side of the circuit to the other is 6 volts. Our animation shows us what's happening to the energy around the circuit. So we should be able to use the animation to guess what the voltage, or PD, is across various things. First of all, what do you think the PD across the battery should be?
6 volts? Oh, it is 6 volts.
The PD across the battery is 6 volts. In fact, the PD between any point, where the charges have all their energy and where they have none, is bound to be 6 volts. Now let's look at current. The symbol for voltage is V, which seems sensible. But the symbol we use for current is I. This is because scientists used to refer to electrical intensity. Current is measured using an ammeter. An ammeter is a bit like a speedometer for charges. Because we need the current to go through our ammeter, we have to break the circuit.
To get in the current to measure it.
And put the ammeter in the way. This is called connecting the ammeter in series.
It has to be connected in a row with all the other things, which is what in series means.
If you look at our animation, you can see that the charges are moving at the same speed everywhere. This means the current is the same everywhere in the circuit. It's difficult to insert a real ammeter everywhere shown. But it doesn't matter where the ammeter is placed as long as it's connected in series.
Everywhere has the same current.
Before we move on to some simple calculations, we need to define voltage and current a little more carefully. Let's look at voltage first. We've said that voltage is the amount of energy that each charge has. Can you remember the units of energy and charge?
I do. I bet you know energy. You probably don't know charge.
The unit of energy is the joule, and the unit of charge is the coulomb. The unit of voltage is the volt.
1 volt.
The number of volts tells you the number of joules of energy that each charge has. In other words, 1 volt is 1 joule of energy per coulomb of charge.
Joule of energy. Coulomb of charge.
2 volts is 2 joules of energy per coulomb of charge. The left-hand side of our animation is at 6 volts because each coulomb of charge has 6 joules of energy. The right-hand side is at 0 volts because each coulomb of charge has 0 joules of energy.
Naught is 0 if you're British.
The middle of the bulb is at 3 volts because each coulomb of charge has 3 joules of energy.
Ooh.
If 3 coulombs of charge had 6 joules of energy, what voltage would that be?
6 joules divided by 3 coulombs.
Well done if you spotted the answer. 2 volts.
Mm.
Watch how the working is done.
Here's some maths.
First of all, let's write down the equation which defines voltage.
Always good start.
V is the voltage in volts. E, or sometimes W for work, is the energy in joules. Q is the charge in coulombs. Q stands for electrical quantity.
Or charge.
Now replace the letters with the appropriate numbers. This is called substituting in the numbers. Make sure you use. Finally, give an answer with the correct unit and underline it.
Volts. 2 volts.
Many people don't like showing their working,
Yes.
but there are some good reasons for doing it.
Like Miss Getz likes it and told you to.
Showing your working makes it easier for a teacher to mark and for you to check your answer. Underlining your answer helps you find it again, as well as helping the examiner.
If you actually put it in a box, I think that's superior.
But there's a much deeper reason
Look at that.
why you should show working. Rather than just saying, "I'm right, you better believe me," you're being more honest. You're trying to persuade others that you're right, but giving them the opportunity to check for themselves. You're showing that you attach more importance to the right answer than simply your answer. Remember that the equation for voltage is V equals E over Q. You may have seen the equation V equals IR. V equals IR is sometimes called Ohm's law. Though it has voltage in it, it doesn't tell you what voltage is really about. You can see V equals IR used in the lesson on resistance.
We'll get there.
Now let's look more closely at current. We said that current is to do with how fast charges are flowing. What we really want to know is how many coulombs of charge pass a point each second. An ammeter acts like a charge counter that restarts its count every second. The unit of current is the amp, short for ampere. 1 amp means 1 coulomb of charge passing a point each second. 2 amps means 2 coulombs per second, and so on. In real circuits, the wires will have different thicknesses in different parts of the circuit. This means that the speed of the charges will change as they move around the circuit.
It's really negligible.
But the same number of charges still pass a point each second. The charges will speed up if the wire gets thinner, and slow down if it gets thicker. In our animations, we make things easier by saying that the thickness of the wire stays constant. This means we only need to think of the speed of the charges when we're talking about current. The 2 arrows point to parts of the circuit where the current is different. Where is the current highest?